Hello everyone, I'm Geoff Brighty and welcome to day 3 of the Blu Hope campaign webinars. Today's theme is innovation for a circular plastics economy, and we follow on from the 2 earlier sessions focusing on how collaboration is really helping to drive that forward. So through the Commonwealth Clean Oceans Alliance, and also the previous presentation that's looking at how the programme brought together called Plastics Pact by an organisation called RAP is looking to bring that collaboration together to get different sectors of business, industry and commercial life to work together to reduce plastic pollution. So we have 2 sessions ahead of us now. The first one is focusing on chemical recycling of plastics, and at 12 noon UK time, 7 PM Singapore time, we have Assistant Professor Suresh Albafathi from the University of Warwick, who'll be talking about his research with in-country partners in Malaysia, looking at coastal pollution and all the elements that are driving some of the acts that unfortunately we're seeing. So in this session, we're going to be looking at some of the technology solutions to recycle plastic waste and really to regain the value of plastic and stop plastic pollution. And specifically, the role of this exciting and emerging technology area of chemical recycling of plastics. I'm delighted to welcome Richard Daley, who is Managing Director of ReNewELP, which is a company from the Mura Group who are co-sponsoring the Blu Hope campaign. And Richard's leading the construction of the world's first commercial-scale plastics chemical recycling plant using hydrothermal technology. Welcome, Richard, to the webinar.
Hi, Geoff. Thank you. Yeah, very pleased to be here.
Thanks for joining us today to go over this thing called chemical recycling. So just by way of introduction to our audience, Richard is a highly experienced chemical engineer. He's worked in senior management positions within a range of operational facilities in UK, Europe and internationally, and particularly focusing on engineering, procurement and construction project delivery. He's a chartered chemical engineer and a registered chartership mentor for the Institution of Chemical Engineers. So thanks, Richard, for joining us. You clearly have a long track record in the area of sort of process engineering and chemistry, but obviously chemical engineering around plastics recycling is something that's really coming to the fore. And obviously, you've been part of this now for the last 2 or 3 years. So just to kick us off, really, and I know you've got slides that you're going to share with our audience. Many of our audience won't really have an idea of exactly what chemical recycling is. So can you just sort of give us a sort of start us off, really? Well, what exactly is chemical recycling in the round, and particularly of plastics?
So yeah, that's a very good question, Geoff. So chemical recycling is a term that's often very widely used, but you find is often very poorly understood. So it may help if I actually bring up my presentation now, if I can share my screen. So hopefully, just bear with me. So hopefully be able to see the presentation just appear now. Excellent. So chemical recycling really is a broad umbrella term that covers a range of different technologies and applications. It's very much a new and evolving industry, and as such, one of the issues for that is there is no real sort of defined definition. So many people, when asked this question, will give slightly different answers, and those slight differences in answers can often have a big impact in people's understanding of what's involved. So what I've included here is a definition from Chemical Recycling Europe, which really is a European association of technology developers, of companies who are very active in developing technologies in this new and emerging field. So this definition describes chemical recycling as any reprocessing technology that affects the formulation of the polymeric waste or the polymer itself and converts these into chemical substances and products for the original or other purposes, but does exclude energy recovery. So effectively, these are processes which change the formulation of the polymer or the polymer itself and make products that can be used again. But crucially, as we've mentioned, really the end products, these are recyclates. This is recycling. So this is not fuels or not recovery to make fuels. So The range of technologies that are covered under this broad sort of umbrella term. There are technologies that are specifically developed to look at individual polymers. So, for example, you have PET. There are companies that look at specifically recycling and depolymerization and really removing additives and colours and impurities from PET. And then you have other technologies which are very much more a broad or a general approach that can take in a range of mixed plastics. So really you have sort of depolymerization, you have thermal processes such as pyrolysis, gasification, and hydrothermal liquefaction or hydrothermal upgrading, which is, I'll take you through in more detail, which is the category that the catalytic hydrothermal reactors or the Cat-HTR process falls into. So these processes such as pyrolysis, gasification, or hydrothermal upgrading are really aimed at sort of general mixed waste plastics. Taking these plastics and actually break the plastics down into the building blocks. And these building blocks can then be used to make new plastics or new products. So it's effectively we're taking in waste plastic and making a feedstock for another process. So this is why you'll often hear the term feedstock recycling substituted for chemical recycling, because some people think that chemical recycling may have negative connotations. But really, there are a range of technologies in this field that are looking at advancing the recycling of hard-to-recycle plastics. That's probably a very, very simple way to sort of describe it, I think.
And there's clearly a range of processes here. I mean, how do you decide which is appropriate? Because I guess each has got its own application or value. So, you know, you mentioned depolymerization from PET, so obviously that's heading to one market, but what about all the rest? How do you decide what is the right process for what situation?
So they're not only are there different processes, there are also different approaches. So you may see some pyrolysis type technologies that are looking to be added on at the end of sort of mechanical recycling. So these processes can be added on to the sort of waste collection industry. So they can then look to convert material where they've been collected at source. And then other processes, very much more chemical processes that would look to integrate into refineries and downstream processes. So really the most appropriate technology really fits in with the country or markets. So the development of the waste infrastructure market or the development of the chemical industry. But really a lot of them are very much adaptable and interchangeable. So there's a range of solutions. There's no one right solution. But there are a range of solutions available.
And from the point of view of hydrothermal liquefaction, which is obviously what we're going to talk about now, the sort of end markets that you're looking at for the products are what? Who are the customers that you're taking that material to?
So we are very much a sort of industrial application. So our liquid products are very much used as feedstocks to refineries. Ideally to make new plastics, so new plastics and chemicals. So when we go through the slides very briefly, there is a little bit on the product, so I'll go into that in a little bit more detail, but very much a feedstock for the chemical industry to make new plastics and chemicals.
So you're sitting between the waste industry and the chemical industry. It's in that interface space between the two.
Yes, effectively what we're looking to do is to take that really hard to recycle waste plastic that we typically see ending up in landfill or incineration as a recovery application, taking that out of the waste streams and converting that into chemical feedstocks for the chemical industry to make new products and plastics.
That's great. Thanks, Rich. I'll let you carry on.
Okay, thanks, Geoff. So we're now to like to give you a bit more of an appreciation or understanding of the Cat-HTR technology. So really, it is in principle a very sort of simple process where we take in end-of-life waste plastic. We then pass it through a cleaning step, and what we mean by that really is we're removing the non-plastic component of the feedstock. So this is glass, grit, metals, and other problematic contaminants. So we're really trying to maximise the plastic content of the waste that we get into our process. We then heat and melt the plastics and mix with supercritical steam. So we'll come on to this more in the next slide. I'll explain a little bit about supercritical fluids, hopefully. So we mix this with supercritical steam, pass it through our reactors. Effectively then we depressurize the process, pass it through a distillation column to separate into products. which are then either stored on site or transported to customers. So fundamentally, it's quite a simple process, but we do use these supercritical fluids. So apologies for the slightly sort of technical nature of this slide, but really in trying to explain what a supercritical steam, supercritical water, or supercritical fluid is, effectively, I thought this would be the most simple way to do it. So if you look on the slide here, you see a phase diagram for water showing pressure on the y-axis and temperature on the x-axis. So there's also 2 points, which is a triple point. So those of you sort of fortunate enough to be able to remember school days may have some familiarity with this, but this is effectively the point at which you can have water as a solid, a liquid and a gas existing at the same point. So you see, if you then increase temperature, you would generate steam or vapor, and you see you generate gas. Or you could lower temperature, increase pressure, and generate a solid. But if you increase pressure and temperature at the same rate or an equivalent rate, you see you reach this point that's called a critical point. And this really is the point at which the water doesn't really exist as a gas or a liquid. Effectively, it exhibits properties of both. So it's what we call a unary system. It's neither technically a liquid or a gas, but it does exhibit properties that are similar to both. So what I mean by that is it can pass through solids like a gas, but it can dissolve things like a liquid. And this is sort of best illustrated by the diagram on the right of the slide, which is showing effectively 4 spheres. So if you look at the top left sphere, you see there is a very distinct liquid and vapor phase within the sphere. And then as you start to heat that, you can sort of start to see steam or vapor being formed on the sort of top right. As this then increases, you start to see the difference between the gas and the liquid phase become less visible. And then in the bottom right corner, you see that there it looks like it's a single phase or a single state. So that's what we call the supercritical state, and that's the conditions that we operate at for the Cat-HTR process. And there are some quite unique properties of steam or the fluid in these conditions that we take advantage of, which we'll sort of go through in this slide. So this is the last of the really sort of technical slides. So really, what we do is we operate in these conditions because the stronger bonds take more energy to break effectively, with the carbon-carbon bonds in polyethylene being the hardest sort of bonds to crack. And we can take in, this process can convert a range of organic materials, so biomass, plastics. So we can take in biomass such as paper and cards, but that effectively cracks sooner, so that tends to crack to gases that we see in the process. And this is one of the reasons that we look to limit the sort of paper or card content, is that it generates gas rather than liquids, which are the saleable products. But effectively under these conditions, we're using steam or this supercritical water as an organic solvent. So very simply, we're using steam to dissolve plastics. But what else happens in these conditions, which is very, very important? Effectively, you have these long polymer chains which are being broken. So you're breaking these carbon-carbon bonds, which forms a very reactive sites. So in other thermal processes, as you break these carbon-carbon bonds, the products of these reactions tend to mix with each other and co-react and mingle and form other unwanted products or other unwanted reactions. Because we're a water-based process, what happens is the water effectively surrounds the polymer chains and really calms these reactions. So as we break the carbon-carbon bond and form a reactive radical site, the water itself donates a hydrogen ion onto that point, which means that the molecule it makes is very stable and doesn't want to react with others. So effectively, we calm the reactions, and the water helps in the conversion and makes very, very stable products. So because we're directly mixing plastics and steam, we have very, very efficient heat transfer as well, which means we can control the reaction conditions very well. So by controlling our reaction pressure and temperature, we can control the rate at which we break the plastics down effectively. And this can help bias our products towards the sort of lighter end, the naphthas, or the heavier end, the sort of waxy ranges of the products. And this really efficient heat transfer also means that our process is really readily scalable. So we can really have these chemical recycling plants that can produce the products at the scale that the chemical industry really wants. And because of the effects of the water calming reactions, helping us control the reactions and helping us make these stable products, we tend to see on a dry ash-free basis sort of over 85% of the mass of plastics that we put in converted to our liquid products. The remainder of this is a process gas, which we actually reuse. We reuse in the process itself. So that really is a very brief overview of the sort of the technology and the principles behind how the technology work. So what plastics can we take in? What material can we process using this technology? So really our feedstock is all plastics, really, so through types 1 to 7. I would say with the exception of PVC. So we would look to remove, limit the PVC content of the feedstock. And that's really because we're making products for the chemical industry. So these products are going into refineries to make new plastics or new oils and new chemicals. So these processes downstream of us, our customers really don't want chlorides or chlorine in the liquids that we make. So that's one of the main reasons that we look to remove PVC. So this is really end of life, so post-consumer plastics. So this is plastic packaging, flexible packaging, rigid packaging. We can take agricultural packaging, agricultural materials. So this is materials that have been through recovery facilities or other processes such as anaerobic digestion, which also leaves mixed plastic material left over. So the message really is the materials that we want are the hard to recycle or difficult plastic materials that are left over after mechanical recycling that we see then blended together to make solid fuels or exported for recycling. And we've all seen what happens with that, with, you know, exactly as we've been with the pollution that we see globally. So this is really hard to recycle material that can't be mechanically recycled. It doesn't need to be segregated. You know, we will convert all polymer types that come into the process. We can take in organics, so food contact, food contamination is not a problem. Paper card is fine, but this biomass converts to gas, so it becomes a question of economics. You know, we're looking to make liquid products, so then to make new products. So if we're making a lot of gas, you know, this is why we would look to limit the paper content of the feedstock coming in. So we're a water-based process. There's no real need to dry. And we can really take in complex, multi-layered, flexible materials. So this is the materials that really have no recycling option at the minute. And so we're looking to divert material away from incineration, landfill, or leakage into the environment.
So these are, so the multi-layered ones are things like crisp packets, sort of food packaging that we're seeing now with foil in it and things like that. Is that the sort of material we're talking about here, these laminates or multi-layered packaging?
Yes, absolutely. And I mean, plastic packaging, particularly in food application, has been developed, you know, to maximise its efficiency in use and not recycling. So there is a big drive to look at the design of this plastic packaging. And what we're trying to show is it doesn't necessarily need to take a step back in efficiency of performance of plastics in use. We can provide a solution that can help recycle complex materials.
And if this stuff ends up in the ocean, I mean, we know there are people, you know, globally. I mean, talking with Paul Rose on Monday, and he was saying that he ran a diving sort of waste cleanup expedition around Windermere and ended up with 11 tons of material that clearly was quite destined for incineration or landfill because it had been out in Windermere on the beaches and obviously got fouled. So can this process also deal with, I quote, ocean plastic that's been out there for a while?
Yes, absolutely. This technology is absolutely ideal for looking at not only solving plastics arising from current use, but also the historical plastic that's also leaked out into the environment. So very, very much, if this plastic can be collected and passed to a facility, a Cat-HTR facility, this is absolutely the feedstock that we will be looking for.
Great, thanks very much.
Okay, so here's a 3D representation of what the first commercial line will look like once fully constructed. So we have a sort of large green building, and as this is being built in the UK doesn't really regulate very well the residual plastic streams that come from the mechanical recycling industry. So there is still a lot of non-plastic material in here. So we do some cleaning up on this plant, and I think that's important to note as well. So in places or countries where the waste infrastructure isn't well developed, you know, we can very easily add on to the front end of this process its own small, compact sort of pre-processing plant to remove the non-plastic material and make it suitable for processing in the main process. So we have plastic cleaning and sort of pre-treatment and storage And then really we then pass this through into the main core technology piece, which is the gold structure that you see in the middle of the plant there. So you can see the overall technology footprint is quite a small area of the overall footprint. Within there are the reactors, the separation column, the boiler. So that's really the core technology process. And then downstream of that, you have the products that are then separated and stored for onward sale. So that was a plan for.
In terms of size, Richard, how would this compare to, say, to the size of an incinerator, for example? Are they much bigger in terms of the scale compared to a Cat-HTR plant?
So these Cat-HTR plants really they're much smaller than the sort of standard incinerator. And as you see, the core technology process is quite a small area of the overall footprint. Really, it depends on the amount of pre-processing that you will need. So to give you an idea of this, with a full sort of pre-treatment or pre-processing, this site is probably 80 to 100 meters long in total by sort of 60 wide. So it's quite a compact footprint for a 20,000 ton a year facility.
So similar sort of size to a material recycling facility or equivalent to waste processing.
Yes.
Site.
Yeah. So whilst we've been developing and commercializing the technology, we've been very much reliant on our technology partners who operate a commercial demonstration and pilot plants out in the Central Coast in New South Wales and Australia. So this has allowed us to run waste plastics through the process and through various pilot facilities that they have on these in Australia, and to generate products. And this has allowed us to confirm the suitability of our products for use as feedstocks to make new chemicals, and also really allowed us to look at different waste plastic, different waste streams, and to confirm our ability to process these at scale. So this has been a sort of a really huge benefit to us. And our technology partners, this process and technology isn't a new process. Originally, it's processed a lot of materials from lignite, brown coal, through to biomass, lubrication oils, and then really it's only been in the past sort of 3 years that we've been really focused on waste plastics. So it's a very versatile technology as well. So we've sort of touched on the sort of feedstock that we're looking for from a waste plastic viewpoint. So we've taken these waste plastics, we effectively pass it through our process. And then as we depressurize at the back end of the process, we effectively use the energy from this depressurization step to flash off a lot of liquids as vapor. So effectively anything with a boiling point below around about 450 degrees will go over as vapor, and we pass this through a distillation column. And this allows us then to separate our liquids out into individual fractions. So we're looking at creating a naphtha, which is up to sort of 210, a distillate gas oil, which is up to 210 to sort of 360 degree boiling, a heavy gas oil, not that dissimilar to a sort of vacuum gas oil from a refinery, up to sort of 450. And then we have this high boiling liquids, which remain as liquids, which is this heavy wax residue type components, where a lot of the solids contaminants, so the plasticizers, the fillers, the very, very fine solids and ash that come in with the plastics, partition to this heavy wax residue component within the process, which is used for sale into the bitumen industry. So it's a sort of bitumen binder or an aggregate. So that's the target market for that. So as we've said, we do crack things at different rates. So we do produce a process gas, sort of C1 through C5 hydrocarbon gas, which is not that dissimilar to natural gas. So we're actually reusing this gas in our process as a fuel to generate the supercritical steam. So this again reduces our reliance on fossil fuels and natural gas. So here is a representation of what these liquids sort of look like from one of the pilot runs. So you see the naphtha are the sort of very sort of low boiling, quite clear liquids. Then you pass through into the distillate gas oil, the waxes, and then really the far right, the sort of very black component is the residue, and that's, as I've mentioned, where a lot of the fillers and solid contaminants end up. So each of these products have established and stable end markets. So the naphtha is very much targeted as a steam cracker feedstock to make ethylene, to make new virgin quality plastics. as is the distillate gas oil. But this can also be used to make solvents and other chemicals and oils. And then as you get through into the sort of more waxy component of this, really you're looking at lubrication oils, wax production. And then for the heavy wax residue, as I've mentioned, really we're looking at the sort of bitumen aggregate. So asphalt and bitumen is the industry that we're looking as the end market for this. So all of these products will be registered as chemicals in their own right with the European Chemicals Agency, allowing you to transport and export these globally. So in addition to taking in unrecyclable waste plastics and making liquid feedstocks for other processes, there are significant environmental benefits from doing this. So really we're looking at diverting material from recovery applications. So this would be incineration, landfill or leakage. So we're moving those up the waste hierarchy into a recycling application. So we're looking to process material that's unrecyclable, a complex material that's too contaminated or too complicated for mechanical recycling. So this is increasing countries' abilities to recycle hard to recycle plastics. So also compared to incineration, which is the current sort of outlet for this hard to recycle material, there are huge environmental benefits from a carbon dioxide and CO2 emissions saving viewpoint. So independent studies, this is for the chemical recycling industry as a whole, rather than this our Cat-HTR specific technology, but under the umbrella of chemical recycling. The University of Delft in the Netherlands, they've done independent work for the Dutch government and have calculated that approximately 45% emission saving compared to incineration. So to put that into perspective, for a single 20,000 tonne per year Cat-HTR facility, you're looking at saving 30,000 tonnes of greenhouse gas emissions, which is a significant saving. So we're again looking to reduce the dependency on fossil fuels. Our products, we're looking to replace fossil fuels and feedstocks, moving away from that fossil linear economy into a circular economy. We recycle a processed gas, again reducing our own demand on fossil resource. And we don't produce a sort of specific waste stream. All of our liquids have end markets and uses. So the solids, the impurities, the fillers, ash that goes into our sort of heavy wax residue is very much a product for the bitumen industry, where the solids, they're used to working with such materials to make roads and things like that. So all products have a home. So significant environmental benefit.
Just staying on this page for a moment, Rich, we've had a question in, just to remind people viewing the webinar, please do send in questions. We've had a couple of questions in, and one is specific that relate to the slide here, which is, says, from the heat or gases from this process, could they be reduced to produce energy? And I guess what you're saying is that any gas generated in this process is reused within the process, but I guess you could take that gas off and save and also capture that if you chose to. But yeah, for the moment, that the process is that is recycled back into the process, so it reduces your demand on the grid.
Sorry, Geoff. There are several options for the gas. Yes, one is we're reusing it in the boilers to make steam. It could equally be used as a fuel for a gas turbine to generate electricity that you could then use in the process, so you could make yourself and help make self-sufficient from an energy viewpoint, from an electricity viewpoint. But also in countries that use gas as a feedstock for steam crackers, it could also be used as an LPG type equivalent and condensed to use to make a steam cracker feedstock to make new plastics. So there are many uses for the gas that we make.
And for the energy being used to create the steam, as well as the ethylene that you're recycling, could you be drawing from say, green energy sources, so wind farms or whatever? Could you be taking recycled energy just to reduce the carbon footprint to pretty much to zero, I guess? Absolutely. Again, this depends on the country or the method of generation that you have in the country that you live in, but absolutely you can take in renewable energy sources to increase the environmental benefit of this process further. Great, thank you.
So from a sustainability viewpoint, we're looking at making sustainable materials, looking away from that linear fossil economy. Our feedstocks are looking to replace hydrocarbons and have a range of existing and established markets. So we're really following the sustainability principles for a circular economy. And really, what's very much worth highlighting here as well is because processes such as the Cat-HTR technology really breaks these polymers down into the building blocks, which are used as feedstock to make new sort of virgin grade material. There is no limit to the number of times that plastics can be recycled in this way. So we can take in waste plastics, we make feedstock that makes new plastics, and at the end of their life, they can then be recycled back through our process, and the process can be repeated. So this is truly a circular economy solution. So I don't propose to go through this slide in great detail, but really in summary, what I wanted to highlight was that we are complementary to mechanical recycling. We look to take in the feedstock, the materials that can't be recycled currently. So these are the problem materials that we see washing up on beaches or being exported and claimed as recycling. We can really help with the reduction measures on redesign and reuse. You know, we can still take complicated material and provide a recycling solution to that. But really, we're looking to create valuable recycled polymers from waste plastic. So I think that probably is a lot to take in, and I know there's been a lot I've ran through. So at this point, I suppose, are there any questions?
Thank you very much, Richard. And it's good to end up on this slide because it does put chemical recycling alongside all the other efforts that people are putting in to create that circular economy. So whether it's on that design and manufacturing side of things, so there's been a lot of discussions, I know, in our space around this about how you can design for recyclability. So, but what I've picked up from our conversation now is that most of this material, even though some of these the packaging is designed to meet other regulations, for example, so food safety regulations are also playing into this space. That actually your process can deal with some of the more complicated plastic packaging, but that doesn't decry the fact if we can find simpler ways of design and recycling for certain applications, then they should be still progress.
Absolutely, yeah, absolutely. I mean, what this slide does highlight is that the whole value chain has to work together to make sure this material is used and dealt with in the most environmentally friendly and efficient manner. You know, everybody has to pull together to achieve this.
And one of the questions we just had in was really looking at the current sort of life stages. Does a typical PET plastic bottle have? And I guess there are people involved with life cycle assessment who could probably answer that more directly. But I mean, I'm given to understand that PET from a mechanically recycled process can sort of go around the loop 3 or 4 times before you start to lose performance, i.e. the color changes, it goes yellow or whatever. So you always have to top up with virgin polymer to keep that going. Is that your understanding? I've just had the question in, so I'm going to put it to you.
Yeah, so when using typical or traditional mechanical recycling, when you're looking at putting recycled content, so if you're recycling PET into new PET, there is a limit on the amount of recycled content that you can put into the new PET, because every time this goes through a cycle, the formulations degrade, and it can only go through 2, 3, 4 times before effectively the properties degrade sufficiently so that it can't be used for its intended purpose. And then it ultimately ends up in a downcycling application. So there are a finite number of times that things can be mechanically recycled, and there are limits on the recycled content of the new material that it makes. And that's a fundamental difference between chemical recycling, because we're actually taking the material back to its building blocks, and then that's used as a feedstock and goes through the full sort of manufacturing process to make virgin quality material. And there's no limit to the number of times that this can be done.
No, and of course for certain applications where the standards for that plastic has to be really high. So I'm thinking of food grade, you would have to have very high quality polymer capability to meet those regulations. So there's, I know in Europe, the Europe Food Standards Agency oversee things like that, and I dare say there's similar ones across the globe. But it's worth just dropping into, you know, it's you know, we are in a very strange time with COVID-19, and we've seen, I'll say, an explosion of use of single-use plastics, and we've seen, sadly, masks and gloves washing up onto our shores. So we've seen a change from people with the on-the-go food packaging and coffee cups, disposing those on the streets, very sadly. But now we're seeing other plastics come forward. So how would the Cat-HTR process work for, say, medical plastics, and could it take medical plastics?
Absolutely. The process can take this material and convert it, Geoff. Yeah. What happens is it becomes a matter of regulation or permitting. Effectively, provided that the waste plastics from medical waste plastics are non-hazardous, so that they've been through some sterilisation process or some process to remove any hazardous classifications of that waste, the actual plastics themselves can absolutely be processed through the Cat-HTR technology. Yes.
So the plastic, the polymers, the feedstock polymers that used in medical applications are not dissimilar to what you're seeing through post-consumer plastics or what's being washed up on beaches. It's the same material. It's just had a different application.
Yeah, correct.
And sort of building out from, I suppose, contaminated plastics, you've mentioned along the way in the presentation that the process can deal with, for example, food contamination, plastics that have come from agriculture, so you might wash off the soil because you obviously don't want that going through your plant. But if they're still not, what we call squeaky clean by any means, so this material still is contaminated to some extent and therefore not suitable for mechanical recycling. But we've been asked to sort of expand a bit more on the ocean plastics. So my understanding of, if you've had plastics either in rivers or in our oceans for a period of time, is that they start to not break down, sadly, but they'll break up, they'll proliferate into smaller and smaller pieces, but also they become what they call biofouls. So they'll have algae growing on them, possibly it could be barnacles and all sorts growing on them. But even biofouled ocean plastics, so that could be nets, it could be sort of packaging that's ended up there, and so on. That can be put through the process, but with some pre-treatment, I would imagine you're not going to put a whole net through the process. You'd have to prepare it in some way. You expand a bit on that.
So absolutely. So things like nets, we have mechanical equipment that feed the sort of melt and feed the plastics into the process. So things where you're using nets and that can tangle with mechanical equipment, we would have to effectively shred or cut the nets down to make sure that we can then process this. But this really, there is the actual what you discussed around the sort of the biogenic content that comes with this is no problem to our process because of our operating conditions. We will convert all organic material, effectively all biomass. The technology itself is far more established, I would say, with biomass applications. So biomass type contamination is no problem to the process itself. Really, with things, it's how you get them into a form that you can get them through the mechanical steps and into the process to be converted.
Yeah. So if this material can be gathered, or I mean, there are various programs globally about preventing stuff going out into the ocean. So I'm aware of something called Networks, where there is a buyback scheme for old nets that can then be converted into carpet, for example. So that's prevention piece. That material could also be converted back into polymer. But it's interesting to think that we talk about, can we go into our ocean and harvest plastic? Well, that's really difficult. There's a range of schemes people are trying to do that, but it's probably more practicable to do it in rivers or in estuaries where the material hasn't yet gone out into the ocean. But there is a value to all the beach cleanups that are going out there. This material could actually end up being recycled. So it's a real cry to those involved with beach cleanups. Yes, this material could be reprocessed.
Because it's all, it's quite easily segregated into plastics. It's mixed plastics, but it's plastics, and it's the plastic content that we're looking to maximise to take into the process. So yes, this is a good feedstock for us. Absolutely.
So we're talking about preventing stuff getting out into the environment, and obviously then can we reprocess plastics that are in the environment that have been out there and have been for sometimes many years. We've seen island communities like Henderson Island receive particularly fishing tackle waste, so big floats and so on that have been out there. So they are, that material could be out there for several years and we could still do it. Let's just go back to one of the very early points here, which is about the sort of conversion ratio of this process. I think, when we talk about how recycling can work, there's an efficiency step, an important efficiency message here. So in terms of the amount of sort of plastic going in, what do you expect to see coming out in terms of polymer in a sort of a mass balance way? What's the efficiency of conversion for the process?
So when we discuss conversion efficiencies, we sort of normalise it by what we'll call on a DAF basis, which is dry ash free. So effectively, we try and normalise it into a term for material that's available for conversion. So if we take in a plastic feedstock that's 30% paper, has 10% moisture, the moisture is lost to the process, or you're taking plastics that have got sort of 30% fillers in there, and that filler material is an inert and it isn't available for conversion into the liquid hydrocarbons. So we normalise it into a dry ash-free basis. So what we've seen from trials that we've run over the past sort of 2-3 years at the pilot facility out in Australia is we've seen conversion rates typically sort of 80-85% plus even higher conversion into liquid hydrocarbons. The rest is the gas. So as we've said, effectively, if you have more paper in there, paper tends to convert more readily and go into carbon dioxide, which you see in the gas stream. So you generate more gas the more paper that you have in there. So you then reduce your sort of conversion into liquids. So, simply what goes out comes in. So you try and maximise the plastic content of the material that you put in.
Right. Well, thanks very much, Richard, for taking us through the Cat-HTR process and explaining this new sector that's coming through now on chemical recycling. Certainly, when you look at the recycling diagram there, you can see how mechanical recycling will sit alongside chemical recycling, so the two kind of go together. And I think for countries that are looking to deal with their plastic waste that is otherwise not being reprocessed, and they want a sustainable alternative, I guess, to incineration, so they need to reduce CO2 emissions. And you mentioned already that this process could be using renewable energy, so they have to get down to sort of a net zero kind of process from a carbon efficiency point of view. That there's really something to look at here. So thanks very much for your time and explaining and the chemistry of it, which even I understood from my school days. So thank you very much for dumbing it down, at least for me. That was very helpful of you. I'd say just one final thing is that if there are any further questions that come through, we will address those by correspondence. So I'm more than happy to respond those through the Facebook Live page. And over the next in the next hour, we'll be talking more about really the plastic pollution issue in terms of what's getting out into the environment, how that's being modelled, understood by Saroush Abdelfathy. So we've gone from the solution piece now to the problem side. So hopefully we'll be able to link those two through this. So we've had a question about the presentations being available. Yes, the presentations are being recorded, and they will be available through the ADEX Facebook Live platform. So and also on the bluhope.org website. So you'll be able to do that. Actually, Richard, just hang on there. We've had another question come in, which is from Gianno dos Passos, who's asked, what are the considerations regarding the fillers and additives usually present in mechanically recycled plastics? Can you deal with it? So it's just to really pick up that point about what happens at the heavy wax end, I think, of the process. Yeah. So I'll let you answer that, and then we'll close.
Because we're taking in these plastics and passing it through our process. Within the plastics, there's plasticizers, fillers, there's ash content, so there's a lot of very, very fine sort of inorganics and solids that are contained within this material. So within our process, we have two ways of dealing with these fillers and solids. One is we actually have the ability to blow down some of the solids that accumulate in the process during the conversion reactions. But also at the back end of the process, we have this sort of flash distillation step, whereby there is a solids disengagement step in the base of the distillation unit, so that allows all of the solids to drop out into this heavy wax residue component. So we see the vast proportion of the solids partitioning with the very heavy, high boiling liquids. And because we're taking over the top fractions as a vapor, effectively these produce very, very clean liquids. So we have two mechanisms for solid separation within the process.
And we haven't mentioned the color of plastics as well as when we've gone away, but the dye stuffs, the carbon blacks and so on, also end up in that fraction as well. So as we know, plastic is a very complicated and complex material with thousands of different formulations. So, but in one step, this material is then this additive material is then dealt with.
Yes. Yeah. Excellent.
Okay.
Well, I hope people understand a little bit more about chemical recycling than they did an hour or so ago. And thanks very much for the opportunity.
Absolutely. Great pleasure, Richard. Thanks for your time. We'll end the webinar now. And thanks again. And we will put the recording up on the Facebook Live page within the next few hours. So thanks to our colleagues here at ADEX. And stay tuned to the Blu Hope channel going through the next couple of days. So thanks again, Richard, for your time. And we'll look forward to hopefully seeing the plant being constructed over the next 12 months. We can actually go and see it. So thank you very much for that.
No problem. Thanks, everyone. Cheers now. Bye.